my apologies for not yet learning Portuguese, but that is one of my goals, and hopefully in the future I'll be able to come back and give my talk in Portuguese. But today, English. Thank you, Professor Lopez, and it's a pleasure to be here at the RSA ANSPE workshop. And today I'd like to give you a presentation on work that we're doing at Florida International University and how it connects with international projects that we have, in particular with ANSP here in Sao Paulo and other collaborators here in Brazil. So that my talk is going to be about managing data-intensive challenges with a science DMZ. DMZ is an abbreviation for demilitarized zone. It's an old concept used from the military to create a boundary to protect resources within a, let's say, an army or a resource area. So my outline is to talk about the data-intensive challenges and working with data-intensive science applications on a campus network, introduce the science DMZ concept, also introduce to you a program from the National Science Foundation for investing in campus network infrastructure, and then a project that we have at Florida International University that is a ward of that CCNIE program. So some background about data-intensive challenges. So many disciplines need dedicated high bandwidth on the campus. For example, high-energy physics, which requires remote analysis of large data sets. Some of the properties, in particular, for example, with the Large Hadron Collider, of which here in Brazil you have Tier 2 facilities in Sao Paulo and in Rio de Janeiro, requiring tens of terabytes of data transfer, being able to work with data distribution across continents, working at very large data rates of 40+ gigabits per second, and these requirements increasing over time. Here you see some achievements that were made last year with the Higgs boson. The same is happening with other sciences such as genomics. The data rates continue to increase, and this is a phenomenon that is beginning to appear more on campuses. You have now instrument data rates that have increased 10 times in the last 5 years. The cost of sequencers have dropped dramatically within the last 5 years, and then these new applications are beginning to multiply more and more and more, and we're seeing this happening on the campuses. So you have also disruptive technologies, not only with genomics, but also with other instruments such as spectrometry. You have also the need to enable remote collaborations, the utilization of visualization platforms to be able to represent these very, very large data sets. It's very difficult to be able to do analysis in traditional ways, and so now you need more advanced instrumentation and tools by which to be able to represent that data. What makes this very difficult is that on a campus, you can't just build the campus network for science. You also have to support the administrative functions of the universities, such as the ERP systems, managing financial data, human resources. So the campus network is a shared infrastructure between scientists, campus IT people that have to manage these resources, the administration. You have security requirements that the university has to comply with that come from the university, from the state level, maybe even the federal level. So it becomes very, very complicated to be able to work with these large data flows in parallel with how a campus is engineered. So the question becomes, how can the campus network be adapted to optimize flows from science applications without impacting the operation of the production networks that support these administrative types of applications. So the Science DMZ is a concept to implement, re-engineer the network in such a way that you can support data-intensive flows and also not disrupt the general purpose functions of the campus. So the idea is to adapt the campus network to optimize these science data-intensive flows without impacting the operation of the production network. The Science DMZ is this concept that adapts the portion of the network, allowing you to engineer the network for science applications, and partitions it so that it does not at all include any of the general purpose networking activities of the campus. You also then have dedicated resources on the Science DMZ for wide area data transfers, which is very important because part of the idea of the Science DMZ is to connect with your external networks to reach resources that science data flows need to reach. So let's look at some of the components of a Science DMZ. You have a border router. You have the connection from a border router to the wide area network. You have a switch in which high performance data transfer nodes are connected to. You see the firewall on the right side that connects to the border router, so there's a way of partitioning the firewall from the Science DMZ. Okay, so the idea is to enable friction-free connections for high-performance data transfers by removing elements that cause friction, such as a firewall. You start to achieve this. So the border router partitions the Science DMZ from the campus network. And the goal is then to support per-service security policy control. And you do that from this border router and your Science DMZ switch router. The other important part is to deploy measurement instruments so that you can have better visibility as to the flows that are occurring and being able to represent them and understand if you're actually making progress, achieving the goals of the Science DMZ. In this representation, there is now support for hybrid network services using technologies such as dynamic circuit provisioning, interdomain controllers, or even open flow software-defined networking. Your switch there can have these capabilities, and you start to be able to then provision end-to-end circuits across the Science DMZ from a high-performance data transfer node through the campus backbone to the border and out into the wide area network. Okay, so I've introduced the concept of a Science DMZ briefly. It's a very important concept. It's becoming adopted rapidly in the United States. I believe there is some projects here as well in Brazil deploying the Science DMZ concept, and I would be very interested in talking to people here who are doing this and see how your progress is coming along with your projects and see how we can collaborate. But one of the things that has been stimulating the adoption in the United States is the work of the National Science Foundation. They came out with this program here called the Campus Cyber Infrastructure Network Infrastructure Engineering Program, CCNIE. It was introduced in 2012, and it welcomes proposals in two categories. One is for data-driven network infrastructure on the campus and for the researcher, and the other one involves proposals for network integration and applied innovation. To date, there's been 47 proposals awarded under this program. So let me tell you a little bit about these two different categories. So with the data-driven network infrastructure, the investments are for making improvements at the campus level to support wide range of science data flows. this could include also investing in the building of a science DMZ. This is one of the things that has been looked upon favorably for proposals that have been submitted. The other characteristic that the program looks for is to enable national and global high-performance end-to-end access, in particular for dynamic network services. This is becoming, the concept of dynamic network services has evolved to now become production on many of the networks that we now work on for research and education. So we now have the capability of supporting what's called hybrid networking services, which support both IP types of services and circuits. And the idea is then to enable rapid, unimpeded movement of these diverse and distributed data sets. So this is where the concept of friction-free comes in. You want to be able to have unimpeded movement of the data across these network connections. The other category, which is the network integration and applied innovation goals, this one focuses more on work that researchers have been doing, in particular network researchers, computer scientists that have been developing and prototyping innovations or tools in their labs, is to now support the deployment and the integration of these innovations that add capabilities to the network. The idea is to enhance end-to-end network cyber infrastructure through the integration of these new technologies and applied innovations. The idea is to start using the campus as a platform for testing and prototyping. And this lines up very well with another project in the United States called GENIE, which means the Global Environment for Network Innovations. The idea is to better connect the campus infrastructure with the GENIE infrastructure to then start extending these capabilities on a more end-to-end capability. So part of what they look for here is integration of networking protocols and technologies with application layer code and processes, and to transition successful prototypes into the SDN, distributed scientific environments, and campus network infrastructure. So the whole idea of this program, this category, is to enhance integration and to allow more prototyping and testing to occur. So we have a project at FIU under the first category, which is the data intensive category. This project was awarded in 2012, and the goals of the project here, or some of the description that we have here, is to support end-to-end science flows that enables a researcher to then start to test and to enhance their science flows on the campus as well as outside the campus. So the idea is to enhance the science DMZ at FIU. FIU actually had a science DMZ before this program started, but it was a very small one, mainly used by computer science and physics. This one now is going to be expanded to enhance and include more disciplines, which I'll talk about in the coming slides. And the idea here is to now extend the science DMZ into the researcher's lab. And so what I'll talk about is the concept of introducing a rack of instruments that extends the science DMZ to the researcher. It leverages resources such as the AMPATH International Exchange Point and a project we have called AMLIGHT that involves Brazil and a number of our partners in Latin America. It also leverages open flow resources to enable SDN end-to-end paths. The idea is to start using the concept of SDN to build these end-to-end paths across the network. Our collaborators on this project are ANSP, CTIO, which is the Cerro Tololo Inter-Organizational Observatory for Astronomy, RMP, the University of Utah, Florida Lambda Rail, Internet 2, and GENIE. Some of the goals of FlowSearch, as I was mentioning in the previous slide, is to enhance science flows to cyber infrastructure resources. at the campus level, which is very important, like for example, the high performance computing resources we have at the campus, any instruments on the campus, regional, national, and international sites that have key instruments and resources that flows go to. The other aspect of the project is to enable researchers to orchestrate and participate in at-scale experiments. This is very important with the goals of the National Science Foundation and the GENIE project, is to enable researchers to do experimentation at scale, which is a very difficult problem to do today with the way the networks have been engineered and the policies and constraints that we have to work within. And then also enable researchers to work with the network as an instrument. This ties in with the at-scale concept and being able to build large-scale experiments. This would allow them to create and observe science flows, give them better visibility as to what their flows look like and if they're working as they should be, and then also to create the opportunity to enhance more closely with our center there at FIU and with the IT organization that manages the network infrastructure. So for objectives of the FlowSearch project, we have science drivers, we have the FlowSearch racks, the Science DMZ, and the campus network. These are 4 levels of the project that I'm going to talk about briefly. So with science drivers, we have high energy physics, optical astronomy, climate modeling, real-time network simulation and emulation, and cloud computing. So we are working with these different disciplines on the campus to roll out, deploy this FlowSearch project as an experiment to see the uptake and adoption of this technology and see if it really does enhance the science flows across the campus, across the wide area to remote sites that they're already collaborating with, but they're using traditional general purpose networking practices. This is a whole new paradigm using software-defined networking. So briefly with high energy physics, as I mentioned earlier, we have a tier 3 cluster at FIU that participates in the CMS experiment. Typically the data is bursty, and it can have 1 to 10 gigabyte data transfers. They use traditional IP as well as dynamic circuits, and the endpoints are to tier 2 sites for the CMS experiment and to CERN. So this characterizes their flows, okay, for the project. And we did that with every one of these different domains. And we're working with 5 or 6 different researchers. And the idea is to put these, what we call FlowSearch racks, in their laboratories that connects them directly to the Science DMZ, separate from the general purpose campus. We're doing the same thing with optical astronomy. We have a professor who is a member of what's called the Southeastern Association for Research in Astronomy. And he works with the observatories, does remote observation with the observatories in Arizona and also in Chile. So he has very long distance connections. His data transfers are not that large, okay, but 2 gigabits in terms of the capacity, but nevertheless they're long sustained transfers that have to be properly tuned. Climate modeling is another application. This will be a new one to the Science DMZ. This one will involve large data transfers from 1 to 3 gigabits. They will use the high-performance computing resources at FIU, as well as accessing very large data sets from the IPCC climate modeling archives. And they will be using dynamic circuits for their flows. Real-time network simulation and emulation. This is one of our computer scientists who has a GENIE rack. He's already been working with the GENIE community for some time. And so he does very large-scale real-time simulation and emulation. So this can generate some very large flows. And he'll be working with the CIARA project here in Sao Paulo, and also with some of the OpenFlow testbeds in Brazil, and some of his collaborators in the United States. With cloud computing, they have a project called Virtualized Infrastructure Systems and Applications. They have collaborations with cloud providers, Amazon, Microsoft, Google, Terramark, the Terramark, NAP, and Verizon, and working with OpenFlow SDN as well. All right, so the next part is very key part to the project is the building and deployment of the flow surge rack. So these flow surge racks represent a fundamental unit of cyber infrastructure in building the Science DMZ. This will be built and placed at the researchers' lab for them to then connect their equipment to this rack here, which gives them capability to work with the traditional Ethernet-based data plane as well as an OpenFlow data plane. It'll have an OpenFlow controller, and it will have monitoring and measurement instrumentation. The whole idea is to provide them with a friction-free connection to the Science DMZ. And this gives you a representation of the rack and what it looks like. This is a half-size rack that can fit like in a corner of a laboratory. This shows you how the Science DMZ is planned for the university. You have a campus building where the flow surge rack is located within a researcher's lab. You have the campus network, and then you have the Science DMZ on the upper right corner here, connecting to the outside world, the Ampath Internet 2 connections here for the exchange point, out to the wide area network. What's important here is at the Science DMZ that you have a switch providing data plane capability. You have the border router, just as you saw earlier. You have the monitoring and measurement capability, providing a management plane by which these flow surge racks can be managed properly by not only the researcher, but also by the IT organization. And you have the separation between the Science DMZ part of the network and the general purpose network with the border router and where the firewalls are. So this is consistent with the general purpose model that has been defined for a Science DMZ. Now this gives you a larger scale representation of what we have in mind. On the left-hand side is the university. It shows a Science DMZ up in the corner there, connecting then to the Ampath exchange point. And from there it extends to the end sites here in South America, as well as to other parts of the United States. The idea here is at-scale experimentation support at a national level as well as global. It leverages the infrastructure that we already have in place from other projects to then deploy SDN capability over it, which is part of the concept of SDN, is being able to enable the operation of multiple networks, partitioning, so that you don't have now any kinds of conflicts between general purpose networking and experimental networking or other kinds of networking. The idea of virtualization at the network layer. And the whole idea then is to support friction-free end-to-end science flows. This is the concept here, and the big challenge of this is being able to measure. This is where we're going to have some interesting challenges, is to have the ability to measure end-to-end these science flows. Our project in year one, this is basically some of the things that we've accomplished. The Science DMZ has been built and has connected to the Ampath exchange point. We have the rack in computer science working across the Science DMZ. The campus network has also been upgraded to support dedicated connections. We are testing the flow switch controller. The one we're using is the Pronto Pica 8 switch. It has a lot of good functionality with the Open V switch software, supports OpenStack and other higher level protocols, supports GRE tunneling as well. We are doing performance measurements testing across the Science DMZ, and we are going to then be connecting the climate modeling laboratory very soon to the Science network. And we've also are connecting the FlowSurge network to the Genie and Internet 2 OpenFlow networks. Some work for year 2 that we have is connecting the remaining FlowSurge racks to the Science DMZ, starting to characterize these science flows with the measurement instrumentation, and also to explore how to operationalize the OpenFlow SDN network to support data-intensive science flows along with the general purpose production flows. This will be a very challenging part of the project. We don't know how to do this yet. This is going to involve some learning. But that's what makes this interesting. This is an experiment. Collaborate with EnSites to optimize the friction-free end-to-end science flows.